So in this order, start now. We have a 30 minutes for your presentation.
Thank you. Good afternoon to the dignitary professor and my dear friends. My research topic based on the title Analysis and Implementation of a Multi-Phase Multi-Level Inverter for Open Winding Load under the guidance of Professor Gabriele Grandi. The aim of my task for the research includes two areas. One is software development in numerical simulation and hardware implementation. As per the software concept, modeling of entire or a comprehensive model of quad inverter plus 6-phase asymmetrical induction motor in open winding configuration has been modeled in Flux software working in MATLAB environment. Then we try to develop a control scheme based on synchronous reference frame which is able to share the entire AC motor drives in each switching cycle with proper multi-level voltage across each stator winding. In particular, when symmetrical and asymmetrical power sharing condition provided by the voltages and current. Finally, we try to investigate the fault tolerant capability of the proposed AC drive system with some proposed post-fault tolerant conditions. In particular, when 1, 2 or 3 voltage source inverter are failure conditions. As per the hardware concern, I have to implement the entire prototype model of a low voltage high current quad inverter system feeding to a 3-phase open winding load. So in case of software, we try to develop the entire AC drive system, but in the hardware implementation, we are done with quad inverter system feeding a 3-phase open winding load, 3-phase open winding load. Then I have to develop the voltage and current sensing unit from the PCB layouts. Then I have to design control boards for 2 DSPs, TMS32F2812 processor. Then PCB layouts for MCDFC channel peripheral interface between 2 DSPs. Then I have to develop a communication channel between 2 DSPs based on multi-channel buffered serial port communication, which is able to control all the 4 inverters with proper PWM communication and synchronization. Then I have to develop a control scheme based on synchronous reference frame using 2 DSP processor TMS32F2812. Then finally I have to validate all the experimental results with respect to the simulation results what we obtained in accordance with the theoretical developments. The key content of my presentation includes an introduction about multi-phase induction motor, multi-level inverter, proposed novel multi-phase multi-level induction motor drive system, modeling of 6-phase asymmetrical induction motor, and includes power sharing management techniques, then post-fault control strategies, then some numerical simulation results and investigations, then experimental results with hardware implementation. Finally, some people conclusion and future work and few proposals. Recent research articles are mostly focused towards electrical drives, especially towards multi-phase induction motor, since they are widely applicable for low voltage, low current applications with low cost semiconductor devices. Also, they are very reliable in case of fault tolerant conditions. Multi-phase induction motors are more advantageous than a conventional 3-phase induction motor when 1 or 2 or 3 phases get faulted due to various conditions. Moreover, they provide system reliability owing to the redundant structure. Also, they reduce the amplitude and increase the frequency of torque pulsations. Also, they reduces the DC current, link current harmonics. Also reduces the rotor current harmonics. This is some of the applications of multi-phase induction motor drives. And most of the literature is addressing towards multi-phase motor are 5-phase, 7-phase and 6-phase induction motor. So 6-phase induction motor can be a dual 3-phase induction motor, an alternative name. Also they have 2 types, one is 30-degree phase shift and 60-degree phase shift between 2 3-phase windings. About dual 3-phase induction motor, dual 3-phase inverter, it acts as a multi-level inverter. So dual inverter are the configurations which are derived from cascaded H bridge converter but slight arrangement of DC sources. Considering 2 conventional voltage source inverters connected across a open winding load, operate each conventional ESI as 3-level inverter. So able to achieve a maximum of 9-level phase voltage across each winding. The advantage of such topology are we can able to have reduced THD in the output, also dV by dt, and additional advantages could be whenever there is a 2 different sources like PV cell or fuel cell or etc., we can able to balance the power. This is a major advantage of this type of topology. Also, there is no circulation of homopolar components since both the DC sources are insulated. So in order also they are cost wise, they are less and their performance are almost equivalent to a traditionally available multi-level inverters. To exploit all these advantages of multi-level induction motor and dual inverter, in this research work we consider a 6-phase induction motor with open winding configuration along with dual inverter to propose a novel topology shown in this slide. So the proposed topology essentially consists of 4 voltage source inverter fed to a 6-phase induction motor with open wind stator connection. And 2 3-phase winding are specially shifted by 30-degree electrical angle, which is clearly depicted in the slides. Then moreover, all the DC sources are insulated, so there will be no circulation of homopolar component, hence no additional compensator is required in the PW algorithm. And able to correlate the power capability of the drive system with 4 inverters. And this system could be more reliable and when 1 or 5 or 3 phases or winding is get open, I mean under faulty conditions. So still is a more compact system able to extend to multiple of 3. For example, we can able to increase to 9 or 12 hands. About space vector transformation, a typical space vector model of a entire AC drive system is depicted in the form of 3-phase space vector, and about multiple space vector transformation is given by the equation 1, which represents represents the 6-phase system in orthogonal subspace, where alpha is nothing but 30-degree and x1, x2, etc. can be a voltages or current. It is proposed by Professor P.Sanjeevikumar. And this multiple transformation can be realized in the form of 2 3-phase subsystem given by the equation 2. So this is the 3-phase transformation variables for the first 3-phase system, and this is for the second 3-phase system. And this was proposed by Professor Gabriele Grandi in the year 2008. And considering the space vector equation can be given by the equation 3. So this represents the 3-phase space vector of the first 3-phase winding, and this represents the the space vector of second 3-phase winding. Substituting the equation 3 and 2 in 1, we can able to find the relationship between multiple space vectors and individual 3 space vectors. So the multiple space vectors are x1, x5 and x3, whereas the individual space vectors are x of 1, x of 2, and they are shifted by an angle of 30 degree. An inverse transformation is given by the equation 5, where dot denotes the dot product and star denotes the complex conjugate. These equations are used in the next preceding slides for the application of control of the proposed AC drive system. This is the model we tried to implement in the software, a 6-phase asymmetric induction motor. It essentially consists of 3 subspaces: space 1, space 5 and space 3. Space 3 is not depicted in the slide since all the DC are fixed and there is no any homopolar component circulation because all are insulated. So we didn't depict the third space because it's absolutely 0. The first phase is similar to a conventional 3-phase induction motor. Corresponding stator voltages, stator flux linkages are given by the equation 6, and corresponding rotor flux linkages and rotor voltage equations are given by the equation 7. Here it only imposes the fundamental components of 12n plus 1 harmonics, and the fifth space is represented just with the leakage inductance given by the equation 8. So it produces only 6n plus 1 harmonics. All the harmonics starts from the fifth will be suppressed in the fifth space, and first phase and fifth phase are orthogonal to each other. So no harmonics present in the fifth space will have interaction with the first phase. So the first phase will have only the torque and flux producing components. Corresponding electromagnetic torque is given by the equation 9. This is the model we absolutely developed in flux numerical simulation software working with MATLAB environment. About power sharing management, already I discussed about the multiple space vectors. Based on the equation 4, we tried to derive the equation of flux producing component from the multiple space vector S1. Is nothing but 3-phase current of the first 3-phase winding and current of the second 3-phase winding shifted at an angle alpha 30 degree divided by 1 by 2. So this is the current going to produce flux as well as the torque. In order to minimize this current, we introduce a sharing variable Ki given by the equation 11. So from this equation we can able to understand 2-3-phase current shares the value with respect to the variable Ki with respect to the multiple space vector I of S1. So this equation can lead to able to find the 3-phase current of the first